Today, let us see how to design a feed-forward controller. We know that the mathematical model of a system may be classified as input-output model. Another one is called disturbance model. The input-output model means this is G of S, GP of S process. For that, if you give input change, we will record the output. If you find for this change, what is the response for that? If you find, then it is called input-output model. That is called Y of S upon M of S, input. Another one is called the same process. For that, we are giving, here we are giving M of S, the output is Y of S. Here also Y of S output, but the input is disturbance, D of S. For that, if you obtain the response, if you get the model, then it is called GD of S. This is called the GP of S. If you obtain the model for disturbance as input, then it is called disturbance model, GD of S. If you obtain the model for input, then it is called process model or input-output model. So we should understand the difference between the two. Both are not equal. That is the first thing we should understand. So if you consider a process, if you want to represent in terms of model, this is the input-output model, GP of S. So if you give input, it will give output. That is Y of S. Another model is there that is called GD of S. GD of S. For that, the input is disturbance, D of S. Therefore, the process can be considered this way. One is what is the response for disturbance? If you get the model, then it is called disturbance model. Give input, that is manipulated variable. Give input and find the response. For that, if you obtain the model, then it is called process model or input-output model. Then what is the expression for Y of S? Y of S equal to GP of S multiplied by M of S. Because the M of S is the input. Manipulated variable is the input. Y of S is the output. Suppose the disturbance also comes in, means we have to add that response also. For that, the model is GD of S, disturbance model, multiplied by D of S, disturbance as input. So this is if you consider both the input as well as disturbance, then this is the expression for output. This is the expression for output. Suppose you want to design a controller for disturbance, that is called a feed-forward controller. Then how to design? This is the process. This is GD of S, GP of S. The output, because of both, will be, you will get as Y of S. Now, the disturbance is entering here. You want to design a controller for this. This is D of S. So you want to design a controller that is feed forward controller. Feed forward controller. That controller output will be added as additional input to this process. Now, what is Y of S? You implemented a controller GFF. Then what is the response? Here we found for open loop. Now let us find with the feed forward controller. If you find that Y of S equal to G D of S G D of S multiplied by D of S. This part. Then another one is D of S through this controller you will get. That is called plus GFF of S. That is feed forward controller multiplied by GP of S multiplied by GP of S D of S. That is another one. Plus if you give input, then you will get you are adding, this is controller output plus input. If you consider this path, you will get M of S multiplied by GP of S. So Y of S equal to, this is because of disturbance. This is because of feed forward controller and disturbance. This is for input. Now let us assume that no input change. Changes in input is 0. Therefore, remaining thing, only because of disturbance you are getting output. This must be equal to 0. The changes in Y must be 0. That way, this feed forward controller has to work. Already there is no input change. There is no change in input. That is equal to 0. In addition, this changes in Y also must be 0. That way, this feed forward controller should work. That's why we are substituting Y of S equal to 0 and MS equal to 0. Therefore, what you will get is G D of S multiplied by D of S equal to minus G D of S equal to plus GF of feed forward controller multiplied by GP of S D of S. D of S getting cancelled. Therefore, GFF equal to minus GD of S upon GP of S. Therefore, the feed forward controller is disturbance model upon input output model minus of disturbance model upon input output model. This is the feed forward controller. Feed forward controller. What is the drawback with the feed forward controller? The feed forward controller will reject the disturbance for which it is designed. It will not reject the other disturbances. That is the drawback with the feed forward controller. So we got feed forward controller equal to minus GD of S upon GP of S. That is the design for feed forward control. Now we'll consider a system whose input output model is 1 upon S plus 1 whole cube. whole cube. That is the input-output model, whose disturbance model is 1 upon s plus 1 to the power 4. That is the disturbance model, d of s. This is m of s. Therefore, if you want to design a feed-forward controller for this, how we will measure the disturbance. If you are able to measure the disturbance, then only we can find the feed-forward controller. Its output will be added to the input. Therefore, GFF equal to minus of GD, that is 1 upon s plus 1 to the power 4 upon 1 upon s plus 1 whole cube, that is equal to minus 1 by s plus 1. So this is the feed-forward controller for this. This is the feed-forward controller. For this, let us see one example. Suppose I'm having a 4-tank process. The transfer function of this tank is s plus 1. For this also s plus 1. For this also s plus 1. The input is m of s is given here. M of s is given here. The output is the level of this tank. Suppose you want to control. Let us have not level. Let us have composition control. Let us have whose model is 1 upon s plus 1. Let us have a composition control. So it is given to a composition controller. Set point is given for the composition controller. Its output is to manipulate. Its output is as to manipulate the input. The output has to be manipulate the input. That's all. Therefore, the process model is GP of s equal to 1 upon s plus 1 whole cube, because they are cascaded. Each one is 1 by s plus 1. That's why its model is G1 upon s plus 1 whole cube. Another, the pre-processing tank is there. Pre-processing tank. Its output also coming to this tank, whose mathematical model is 1 upon s plus 1 again. The disturbance is entering here. The d of s is entering here. D of s is entering here. Therefore, if you consider the disturbance model, then it is 1 upon s plus 1 to the power 4. 1 upon s plus 1 to the power 4. But if you consider the process, that is 1 upon s plus 1 whole cube. Therefore, if you want to design a controller, any change here, if you notice any change here, you want to design a controller for this, then you have to measure the disturbance. You have to put a feed-forward controller here, that has to be added to this input, input. That's all. Now we have to find a GFF. The disturbance model is 1 upon s plus 1 to the power 4. Process model is 1 upon s plus 1 whole cube. Therefore, GFF equal to minus GD of s upon GP of s. That is equal to minus of 1 upon s plus 1 power 4 whole divided by 1 upon s plus 1 whole cube. That is equal to minus 1 upon s plus 1. That's what we have seen here. So GFF equal to GF of equal to 1 upon S plus 1. That minus sign we can put here. That minus sign we can put here. If you put a plus sign here, you would put a minus 1 here. That's all. Minus 1 by S plus 1. That way, we can design the feed forward controller. Now let us simulate this feed forward controller in MATLAB. Process consists of 3 tanks only. 3 processing tanks. Each one is of model 1 by S plus 1. So 3 in cascaded. So if you put a conventional controller, what you will do, you will put a PID controller. You will put a PID controller, and we know that the tuning parameter will be defined. What is the tuning parameter for this? The process is 1 upon S plus 1 whole cube, 1 upon GP of S is equal to 1 upon S plus 1 whole cube. That is 1 upon S cube plus 3S square plus 3S plus 1. So if you find, to find ultimate gain, let us use Routh array 1, 3, 3. This is open loop transfer function. What is closed loop transfer function? The gain is K. Therefore, what you will get is the closed loop denominator polynomial equal to numerator plus denominator. Already we have seen this in the control system. That's why S cube plus 3S square plus 3S plus K. KC is in the numerator. This is open loop transfer function. If you put this in closed loop, you will get 1 plus K, KC. Therefore, here the constant term is 1 plus KC. So S power 1 is 9 minus 1 plus KC. S power 0 is 1 plus KC. Now, to find K max, we have to use the S power 1 row. We know. Therefore, 9 minus 1 plus KC equal to 0. Therefore, K max, KC equal to 8. KC equal to 8. K max equal to, that is K max equal to 8. Ultimate gain is 8. What is the period of oscillation? For that, we have to consider the second row. That is 3S square plus KC equal to 8. Therefore, plus 9 equal to 0. Or S square equal to plus or minus 3. Or J omega square equal to plus J omega equal to plus or minus J root 3, or omega equal to root 3. Omega equal to what? 2 pi F equal to root 3. Therefore, F equal to 0.27 566. Therefore, TU equal to 1 by FU. FU equal to ultimate period equal to this. Therefore, TU equal to 3.627. So we got TU equal to 3.627 and K max equal to 8. So now we can find the tuning parameters. So now we'll simulate this. So what you will get for PID controller, the tuning parameters for PI controller is 8 is the ultimate gain multiplied by 0.45. So here KC into T, KC by TI. TI equal to what? TU divided by 1.2. Therefore, 8 multiplied by 0.45 divided by 3.627 multiplied by whole divided by 1.2. That comes to numerator. That's why multiplied by 1.2. So we entered the tuning parameters. What is feed forward controller? Feed forward controller is minus 1 by s plus 1. That is the feed forward controller. That also we entered here. We'll remove the link for PID controller. So let us have only, we removed the link for PID controller, feedback controller, only feed forward controller. And we are going to give the disturbance. Disturbance is given at step time is 0, final value is 1. Let us give at 0th time. Okay, let us give at the 0th time. Here also let us give at 0th time. And we are not going to test for servo response. Therefore, final value for servo response is 0. Final value for servo response is 0. We are going to test only for disturbance. Disturbance is here. What is the disturbance model? 1 by s plus 1 to the power 4. 1 upon s plus 1, 1 upon s plus 1, 4 times. That is disturbance model. Process model is 1 upon s plus 1 whole cube. So here, this is the feedback controller. This is feed forward controller. Feedback is removed. Feedback is removed. No connection for feedback. Only feed forward controller is there. Feed forward means no feedback. The feedback is not used. Only forward path is there. We are measuring the disturbance. We are giving to the controller, feed forward controller. That is minus 1 by s plus 1. And it is given as input. That's all. No change in input. No change in input. Because we are working with only feed forward controller. Now let us check the response. Now let us check the response. You see that feedback controller is red. Feedback controller is red. That also controls. It rejects the disturbance, but so many oscillations. So many oscillations because it tried to control after the effect made in the output. Because because of the disturbance, the process is deviated. After that only the PID controller will take action. That's why this much time. But you see the feed forward controller, no disturbance is injected into the process. It remains 0. It remains 0. What is we gave there? What is the input here? Only disturbance is given. No input is given. It should be at 0 only. It should be at 0 only. Or here you can give 0 as input. You can give 0 as input here. No input is given. Only this disturbance is entering. Disturbance control as well as disturbance is entering here. That's why you see the response for this. No effect in the output. Because feed forward controller rejected the disturbance in the beginning itself. It rejected the disturbance in the beginning itself. That's why no effect on the process. But here we have to obtain the mathematical model of disturbance. From that only we are obtaining the feed forward controller. How it is designed? GFF feed forward. GFF feed forward controller equal to GD minus GD divided by GP. GD we got perfect model 1 by s plus 1 to the power 4. GP is 1 upon s plus 1 whole cube. If we divide that, we got 1 by s plus 1. We entered. That's why there is no disturbance. But it is not possible. It is not possible to get the perfect mathematical model. We can get approximate model only. Suppose I got approximate model, not perfect model. The approximate model for this disturbance is approximate model for the disturbance is approximate model for the disturbance is GD of S. GD of S obtained, that is 1 upon 0.9 S plus 1, 1 upon S plus 1 whole cube. Actually, what is the correct model? 1 upon S plus 1 to the power 4. But I got poor model because it's not possible to get the exact mathematical model. Practically, it is not possible. We can get approximate model only. This is the exact model, but we got approximate model. This is approximate model. Approximate model we got. GP of S we know, that is 1 upon S plus 1 whole cube we got. Therefore, GFF equal to 1 upon 0.9 S plus 1 multiplied by 1 upon S plus 1 whole cube whole divided by 1 upon GP of S. GFF equal to what? GD of S upon GP of S minus whole cube. These two getting cancelled. Therefore, 1 upon 0.9 S plus 1. But real disturbance model, if you see, 4 tanks are in series. Each one is S plus 1. We modeled this as 1 by 0.9 S plus 1. That is the error in that modeling. Actual model is 1 by S plus 1. This is actual. But we modeled it as 1 by 0.9 S plus 1. Error. That's why the feed-forward controller we got is 1 by 0.9 S plus 1. Now let us check for that also. Therefore, GFF equal to GFF equal to 1 by 0.9 S plus 1. Now let us check whether it works for approximate model or not. So we have to enter here instead of 1.9, 0.9. Yes, we entered 0.9 instead of 1 by S plus 1. It is approximated to 0.9 S. Now let us check the response. Then also it controls, but better than feedback controller. But some undershoot is there. But it gives better response than if you see the ISE IAE. Definitely it will reflect the response because it has large value of ISE, because it has large oscillations. But the feed-forward controller, then also it controls, but has better dynamics than PID controller. Let us put further worsen this modeling. Now let us put 0.5. For that also how it works, because we poorly modeled, that's why we got 0.5. Then also it is better, it quickly settles than a feedback controller. You see the response, even it is 0.5, it works better. Even it is 0.5, if you poorly model, response will be poor, but anyhow better response than feedback control. But the problem with this is it won't work for other disturbances. Now let us make other disturbance here. We'll give some other disturbance here. Let us check whether it works for that or not. I'm giving one more disturbance. That is some other disturbance that we are going to give. Here also we are going to give the same. Here also we are going to, for feedback also we are going to give the same. Yes, we gave. The disturbance Step time is 0, final value is 1. But we are not going to give this disturbance. This disturbance is not coming. So we have to check for some other disturbance. That's why we'll make it as 0. We'll make this disturbance 0. We'll make this disturbance 0. Now let us check. Some other disturbance is given. Let us check. What happens to the new disturbance? Feedback controller bring back the process to again 0. Feedback controller bring back the process to 0. But some other disturbance came. That's why that controller doesn't work. It deviate the process to 1. It deviate the process to 1 and remains in 1. Therefore, feedback controller will not work for other disturbances. Will not work for other disturbances. That's why we should not use the feed forward controller alone. If you use the feed forward controller alone, it will not work for other disturbances. That's why we have to use along with feedback controller. That's why now we connected the feedback controller. The feedback controller having the tuning parameters. Yes. Feedback. Along with the feedback, you can use. Now, let us check for other disturbances. Definitely it will work because feedback is there. What happens? Both will be same. For that other disturbance, both will be same because both responses will be one over the other. Yes, one over the other. Because PID controller is there, that's why that takes care of the other disturbance. Now we will check for this disturbance. We will remove this other disturbance. We will remove that other disturbance that is removed, and we will give the disturbance for which we designed a feed forward controller. That disturbance we are going to give. That disturbance we are going to give. We are not going to give the other disturbance that we made 0, but we are going to give the disturbance for which the feed forward controller is designed. For which the feed forward controller is designed. Yes. Now, let us check one more time whether I give correctly. Yes. Disturbance is given for which the feed forward controller is designed. This other disturbance is removed. The other disturbance is removed. Yes. The other disturbance is removed. Here also, we are giving the disturbance for which the feed forward controller is designed. Now let us check along with the feedback controller. You check yes, it gives better dynamics. What is the controller we gave? Controller we gave is 0.5. 0.5 we saw large deviation earlier, because now we are using along with the feedback controller. That's why it gives better dynamics. If you put 0.9, you can notice that change. If you put 0.9, small error in the modeling. Small error in the modeling. If you see that small error in the modeling, it gives better dynamics. Earlier we saw large deviation. Now small deviation only. We are using along with the feedback controller. The dynamics is better. If you see ISCIAE, it'll What is that? Math. So you see that with the feed-forward controller, it gives better dynamics. Better dynamics. Even if we give 0.1, let us give deliberately worst model 0.1. For that, what is the dynamics? Even then, here the IA is 1, here 0.8, here 0.1, here 0.05. Even if we model very worst, that is, one is modeled as 0.1, very, very poor modeling. Even then, it gives better dynamics. Even then, it gives better dynamics. Therefore, if you use feed-forward controller along with feedback controller, it will give better dynamics. That we can notice. Now let us check for servo response. So far, we tested for disturbance. Now let us check for servo response. The final value is 1. So far, we have not yet tested for final value is 1. Here, then we have to give the disturbance after long time. That's why let us give at 50. Here also let us give the disturbance at 50. The disturbance is given at, there is no difference in servo response. There is no difference in servo response, but regulatory response, this gives better dynamics than this. We gave 0.1, 0.1. We have not yet changed. That's why if you see the if you see the ISE 5.7, here 5.9. This is ISE 1.9, here 2. So even it's here I changed it, Yes, even 0.1, the ISE gives better dynamics. If you put 0.9, see the response with the 0.9, poor modeling, but 4.9 here 5.9. You see the response. IAE is 4.9. Here 5.9. Here IAE, IAE is 4.9 and 5.9. ISE is 1.9 and 2. So even that you can see here. So here you notice that insensitive to disturbance, small deviation is there. So if you model well, you will get a better dynamics. If you use along with feedback controller. Now we will give all the three disturbances. Now we will give this at where it settles. All the three, let us give. It is settled about 40. So we'll make 40 and it settled 50, 80. So we can give at 80, we can give. Okay, now let us give this disturbance at 40. This at 80. All the three we are going to give. This at 80. This disturbance at 40. And this disturbance, some other disturbance, that is at 80. You see? You see? Some other disturbance, the controller, the feed-forward controller designed is not for the disturbance. That's why it is not working. Both are identical. Both are identical. Only feedback controller is working. Feedback controller is working. The feed-forward controller is not working. Therefore, both are identical. Both because it is not the disturbance for which we designed the feed-forward controller. But here, the second disturbance, the first disturbance is we have feed-forward controller. That's why there is no disturbance here. But the second disturbance is we are not having feed-forward controller. That's why it is not working. That's all.